All right, IB, we've made it to the very last section for Chapter 11, which is Section E, solving trig equations that are in quadratic form. A little different to the equations we were doing the other day. So we're noticing now that we're going to wind up with a quadratic. So if you take a look at this cosine squared plus cosine, really, we could, I'm going to put this in a little brain bubble here so we can think about it. But really, if we replace cosine with, let's say, a letter a, we're really looking at an expression that's representing 2a squared plus a equals 0. All right, so throughout the next couple examples, just be thinking about how you can represent these trig equations without trig functions. So let's say they were just a's or b's or something else. So for this one, we notice that we have a common factor of cosine. So I will factor out cosine x, and I'll be left with 2 cosine x plus 1. Since we now have 2 factors, cosine x is 1, and 2 cosine x plus 1, we are going to set each one individually equal to 0, because we know that cosine x times 0 would make 0, or if 2 cosine x plus 1 multiplies by 0, I would wind up getting 0. So one of these factors needs to be equal to 0. So let's see what possible x values we could have if cosine x equals 0, and also if 2 cosine x plus 1 is equal to 0. So we now are going back to the trig equation, similar to what we wound up solving just a few sections ago. Cosine x right now is already isolated, so when does cosine wind up equaling 0? We're thinking back. Cosine as your x value. So cosine would be 0 at pi over 2, or 90 degrees, and also at 270 degrees, since we're within 0 to 360. So let's go ahead and answer our 2 values here, 90 degrees, answering in degrees, since the question's asked in degrees, and 270 degrees. In the second equation, 2 cosine x plus 1 equals 0. We need to isolate the cosine. So cosine x will be equal to negative 1/2. For this one, I'm going to have to think about my 30, 60, 90 triangle and think about my ratio for cosine as, all right, so if this is 30, here's 1, root 3, and 2. So cosine would have to be up here. We'd have to be thinking about an angle in this corner, so that my adjacent and my hypotenuse would be 1 over 2. So I'm thinking of a 60-degree reference angle, and cosine is negative in the second and in the third quadrant. So I'm thinking of 120 degrees and then 240 degrees. So x is equal to 120 degrees. That would be a 60-degree reference angle in the second quadrant, and then 240 degrees would be a 60-degree reference angle in the third quadrant. So I have now included all of my answers, so therefore x is going to equal 90 degrees, could be one solution, 120, 240, or 270, and that would include all 4 possible values of x in order to make this original statement equal to 0, and making that statement true. All right, in the second example, we have 2 sine squared x minus sine x minus 3 equals 0. Hopefully we're identifying already that this looks like a quadratic. And if we replaced sine x with a letter, so let's say w, we would really just be looking at 2w squared minus w minus 3 equals 0. So we have 2 ways to factorize this, 2 ways that we've talked about in class. One is factorizing by splitting the middle term. So we split up negative w as negative 3w plus 2w. Again, we're thinking about ways that as we factorize, we'll have 2 common binomials, so 2w minus 3, 2w minus 3, and this is factorizing by grouping. And the other way is sliding and dividing. Where you just momentarily think of your 2 and your 3 as the factors that you need to try to split, again, kind of like you're splitting your middle term. So we're still using 2 and 3 just as we did from above. However, we momentarily slide the 2 down to multiply by the 3, allowing us to factorize just w squared minus w minus 6, so we don't have that leading coefficient. And then because we've multiplied it down originally, we had divided it back in. Obviously, we can't just get rid of it. So you're really doing the same math, just writing it out a little differently. Either way, you're going to wind up with 2w minus 3 and w plus 1. So remembering, practice your factorizing because it'll come in handy for all of your quadratic questions. And then again, comes back throughout IB in several different places. So the reason why I have this off on the side is because remember, this is side work. My question is actually asking me to factorize 2 sine squared minus sine x minus 3 equals 0. So now thinking back to w being actually representing sine, let's go ahead and write our two factors using sine. So it's 2w minus 3 is actually going to be 2 sine x minus 3, and then w plus 1 will actually be sine x plus 1. All right, so however we wound up factorizing, let's go ahead and just make sure that the next line of work actually has our factorized trig equation, which is what we originally started with. So now following back through, again, we have two factors. We'll set both of them equal to 0. So we'll take 2 sine x minus 3 equal to 0, and then sine x plus 1 is equal to 0. Isolating sine, we have sine x equals 3/2, and sine x is equal to negative 1. So just taking a look at our two different answers, if we try to inverse sine and 3/2, let's just think for a moment. Where in our unit circle do we wind up having a ratio of 3/2? Okay, if we remember our sine graph, if we think about the curve of our sine graph, the max our sine represents our trig ratios as goes up to 1, and the lowest value is actually negative 1. So sine x is always between positive 1 and negative 1. So we actually do not have a ratio that is higher than 1 or lower than negative 1. So automatically when we see a value that we're trying to identify an angle for to get a trig ratio of more than 1 or smaller than negative 1, it's a big red flag, okay? Not going to work. So there is actually no solution with this possible factor being set equal to 0. So we are not going to get an answer from this factor. So let's take a look over at sine x equaling 1. We know that sine x is equal to 1 when x is, and we're looking between negative pi and pi. So we want to include just pi over 2 on this one. So at 90 degrees or pi over 2. All right. And we actually will not have, if we're going from negative pi, so negative pi would be this direction. Here's negative pi to positive pi, this direction. All right, the only time that sine x will equal 1 is at pi over 2. So I've included all possible values in this interval. All right, so this question 2 from your textbook, you guys are going to be practicing a bunch of these in class. However, we're going to choose one just because it's a little bit different and we have to kind of think a little bit outside the box in order to approach it. So sine x plus cosine x equals square root of 2 as it stands. I can't do a whole lot with it at the moment. So think about what we've been learning over the last few days. I can factorize if I could. There's really nothing to factorize here. I could try to use one of my trig identities. Okay, that's another option. So remember, your formula booklet has all of your trig identities in them. You're not expected to memorize them. However, when they're in front of you, do you know how to use them and can you use them? So I notice that I have a square root of 2 here, and I've got sine x plus cosine x. I know if I square them, I've got a couple trig identities that include sine squared and cosine squared. So let's start by actually squaring both sides. So again, whatever I do to one side, I'll do to the other. So I'll wind up with sine x plus cosine x, quantity squared, equals the square root of 2 squared, right? Sine x plus cosine x squared means that you're actually multiplying, we know this, sine x plus cosine x twice. So that means I will have to expand this. So if I actually multiply that out, I wind up with sine squared Always make sure, a couple questions over the last few days, make sure sine squared x is sine x quantity squared. Please never write sine x squared. That is not the same thing. All right, so just a side note as I've been looking at work over the last few days. Okay, just keep that in your head for future. All right, so back to our question. Sine squared, sine times cosine and cosine times sine. That means I'll have a double of sine x cosine x. And then I also have cosine squared. Okay, that helped me get rid of the square root. So now I have a 2. It also gave me a sine squared and a cosine squared. So I know that sine squared and cosine squared equals 1. So now I'm looking at 1 plus 2 sine x cosine x. I also know that 2 sine x cosine x is sine 2x. So I can also replace 2 sine cosine with just sine 2x. So now I have 1 plus sine 2x is equal to 2. Now I can think back through my 4 steps because I'm ready to start solving. I've simplified this question down. I'm just dealing with sine now, which is great. So sine 2x is equal to 1. Now let's look back up at our interval. Because I've got a double angle, I do have to adjust my interval accordingly. So I'm looking at x is between 0 and 2 pi inclusive. So if I'm going to change x to 2x, that means I'm going to come all the way out to 4 pi. And there we go, 0 will stay the same. So let's just continue. Inverse sine, okay, at 1. So sine is 1 at pi over 2. And then as I'm going all the way out to 4 pi, so I've got pi over 2, I have 2 pi units later. So I've got 5 pi over 2. All right, if I go another 2 pi units later, I'm going to wind up at 9 pi over 2, which is just beyond 4 pi. So I'm going to stop at pi over 2 and 5 pi over 2, divide by 2, and I'll get pi over 4 and 5 pi over 4. All right. Now, a little different with this question. Because I wound up squaring at the beginning, remember when you square, you could have a negative or a positive, and when you square it, it's still going to come out as a positive. So with this question, because I'm dealing with squares, I do have to take a few test values and just make sure that if I substitute x as pi over 4 and 5 pi over 4, it actually does work. So let's test our solutions. All right, and we're going to test our solutions by letting x be pi over 4, and we're also going to let x be 5 pi over 4, and we'll substitute back into our original question, which was just sine x plus cosine x equals root 2. So is that true? Does sine of pi over 4 plus cosine of pi over 4 actually equal root 2? So again, sine at pi over 4, remember that's a 45-degree reference angle, so you're looking at your 1, 1, root 2 triangle. So sine would be 1 over root 2 plus cosine at pi over 2 would be the, pi over 4, excuse me, pi over 4 would also be 1 over root 2. So 1 over root 2 plus 1 over root 2, we're looking at 2 over root 2. And if I wind up rationalizing the denominator, so multiplying by root 2, okay, then I actually wind up with 2 root 2 over 2, or just root 2. So yes, pi over 4 does work. Let's try 5 pi over 4 as well, just to test both of our solutions. So sine of 5 pi over 4 plus cosine of 5 pi over 4. All right, so now we are at 5 pi over 4. We are going to be 1, 2, 3, 4, 5 down here in the third quadrant. If I'm in the third quadrant, Cosine and sine are both negative. So negative 1 over root 2 plus another negative 1 over root 2 is going to give me a negative root 2. All right, so no, this actually does not wind up giving me an answer that would satisfy this original question. So I'm going to toss out the one value that I got at 5 pi over 4. Okay, so x equals pi over 4 is my final solution. All right, guys, see you later.